Today we will have a short class. We started to design steel beam. Actually, we have two cases or two scenarios. The first one, your steel beam what is the unsupported length of your compression flange, which called LB, and supported length of your compression flange. This length can let you know if we have issue with lateral torsional buckling or not. If not, which means your unsupported length smaller than LP. As you remember from last time, we have two terms, LP and LR. These two terms from tables based on the cross section. Each cross section has two values for LP and LR. If your unsupported length of the compression flange less than LP, you are good. Your cross section is compact section. We don't have issue with lateral torsion buckling. Everything is okay. Your nominal moment is the same like plastic moment, equal F yield ZX. If you would like to get your design moment, just multiply by phi to get your final design bending moment. That's all. So LB may be 1 feet, 2 feet, 3 feet, whatever, but LB is smaller than your LP from your table. Sometimes the problem or your structure, this steel beam is supported by concrete flange. If you have concrete flange at the top of this beam, that means your unsupported length of your compression flange equals 0. Actually, every single inch of your flange is supported in your concrete slab. So you are in this case. The second case, your unsupported length LP in between LP and LR, smaller than or equal. So we have some concern regarding lateral torsional buckling. We can get your nominal moment by three options. First option, you can use this equation, or you can use this equation, or we can use chart. First equation, we need a term CB M plastic equal F yield CX. MP the same, 0.7 F yield based on what type of steel, SX from table. We have two terms from your table, sometimes ZX, sometimes SX. Both of them are section properties. But the first one called plastic section modulus. The second one, elastic section modulus. It's a section properties. So based on what type of cross section, what is the name of your cross section, from your table, you can figure out what is the value of ZX, if you would like to get it, or what is the value of SX. LB, unsupported length. What is the unsupported length of compression flange? LP, LR from your table. You can get your value, but be sure your value must be smaller than or equal MP, plastic moment. CB is a factor based on what type of fluid do you have and how many points you are supporting your compression flange, maybe at the beginning and the end of the beam only, maybe at the beginning, at the end, at intermediate. So what type of, how many supports for the compression flange, what type of fluid, you can figure out what is the value of your CB. Or you can use your table also, but different equation, a different equation. Your design moment equals CB, the same, phi M plastic minus phi PF times LB minus LP. Or we can use chart. If you remember, we have chart. At this location, what is the value of your unsupported length? Go up until you hit your name of cross section, W15 times 25, for example. At this location, go horizontally. Here is your phi MN, your design bending moment. That's all. The only issue with this chart, we don't have all cross sections, just few of them in this chart. But if your cross section not included here, go ahead and use this equation or go ahead and use this one. We covered this example last time. We have another example here. Determine the flexural strength. What is the design bending strength for W14 times 68 steel A992 subject to continuous lateral support. The second case, we have an embraced length of the compression flange equal 20 feet. Let's start with the first case. We have continuous lateral support. Continuous lateral support, that means this wide flange 14 times 68 is supported by concrete flange or concrete slab. So your LB equal 0. We don't have unsupported lengths because we have continuous lateral support. So I think LB will be smaller than LP. So in one equation, your design bending moment equal phi F yield ZX. That's all. Very simple equation. Very simple step. So phi 0.9, F yield based on what type of steel will be 50. ZX, go ahead, open your table for W14 times 68. What is the value of ZX?
115.
115. 115. So get your number, 0.9 times 50 times 115, something around 5,000.
5,175. 75, I think.
5,100.
75.
Your units?
No,
5,175.
5,175.
1,575. What's wrong?
5,175.
5,000. Pay attention, people, please. 0.9 times 50 times 150. Okay. Your unit is very important. Go back to your unit of your material. KSI. ZX N inch to third. So your final value will be kip inch divided by 12. We like it to be kip feet because our unit in structural analysis kip and feet. 431.25 kip feet. So this beam from this material of steel can support bending moment equal 431.25 or less. Second case, we have unsupported length LB equal 20 feet and given CB equal 1. Anyway, I cannot say we will use the second option or the second case. I'm not sure yet. What is the value of LP? What is the value of LR? Go back to your table. For section W14 times 68, go ahead. What is the value of LP?
8.69.
8.6 feet. What is the value of LR?
29.
29 feet. So, what is the relationship between LB and LP and LR? In between or smaller than LB or greater than LR? What's your case? I think LB in between. If your LB unsupported length in between, so we have three options. First option, you can use this equation. Second option, you can use this one. Third one, you can use your chart. I think let's start with the chart. Maybe we can find your cross section. What is what? CB? What's the question?
Is it supposed to be CB or LB?
Which one?
The example 3.
This value LB, 20 feet, and supported length.
What is CB?
No, CB is a value given.
Oh, and the table's just for CB for one.
Oh, okay.
CB is a factor given in the problem,
I see.
equal 1.
I got it.
That's all. So let's start. What is the name of your cross section?
14 times.
14 times 68. Done. I will open my chart first. Design of beam.
See you code.
Go down. Do you have here 14
Yeah.
times 68?
By 435.
Which one?
By
14
435.
times 61.
Oh,
Up top. By 435 on the left side.
It's like weird.
Left.
to-
Left.
Yeah. Almost more left. More. Right.
14. I cannot see it from
Do you see
here.
435 or
On the left side.
where the bending moment is at?
Way up top, right
Up,
there.
More,
up,
a
up.
little bit up.
Up.
Yeah, right there.
1468. I think, which one? This one, maybe. What's this one?
I think it goes with the dot.
Or, I think, maybe, no, this one.
Yeah.
Here you go. Yeah. So, using your unsupported length 20, something here, go up until you hit your cross section, go horizontal. Here is your design bending moment. something around 345. Phi MN 345 kib, I think, feet. If you did not find your cross section here, go ahead and use your equation. Let's try to use our equation. What will happen? Let's start with this equation. Your design moment, phi Mn equals Cb, phi M plastic minus phi Bf LB minus LP. Open your table, search for W 14 time what? 68. Okay. 14 times 68. Go down. 14, no. 14 times 68. Here you go.
It's on.
This one. Uh, 1468. Can you see this one? Okay, go ahead. What is the value of CB given? 1. Phi M plastic is given directly from this table. You can figure out what is the Phi M plastic.
431.
Do you agree?
Yes.
What is the value? 431. Minus Phi is 0.9 time BF. For this cross section, your value of BF according to LRFD equal 7.81 time LB, which is 20 feet, minus LP. What is the value of LP? 8.69.